So I'm going to be introducing the next two speakers, and Paul Anastas is actually called the father of green chemistry. He coined the term in 1991, and is currently the professor in the practice of green chemistry, and he's also the director of the Center of Green Chemistry and Green Engineering at Yale University. And the title of his talk today will be Transformative Innovations Needed by Green Chemistry in Sustainability. So please welcome Paul.
Well, thank you. This is a wonderful honor. Thank you, Mark. Thank you, Dorothy, for having me. Thank you to the New York Academy of Sciences. This is an enjoyable opportunity. I've been having a wonderful day this morning, listening to all our talks, and I'm going to try to focus on this emerging area of green chemistry. Some of you may be more familiar with green chemistry than others. But it really does boil down to part of the very nature of chemistry and why so many of us in this room love chemistry, which is that it has two components to it. There's certainly the aspect of chemistry that studies the world as it is and seeks to understand the world as it is. And that has largely been how environmental chemistry has been perceived historically, of trying to understand the different chemical processes that are taking place in the natural environment, and also how our environment is being impacted by humans. But there's the other part of chemistry, the creative or creating side of chemistry, that introduces new substances into the world, substances that are the basis of our economy and our society. And those, of course, have a significant impact on the world. And thinking about how these substances are going to be able to be designed, manufactured, modified, so that they are fundamentally sustainable, is what I'd like to chat with you a little bit about today. Because when we step back and take a look at some of the grand sustainability challenges, we can all come up with our own list. But certainly the great challenges of energy, moving to renewable and sustainable sources of energy, water quality and quantity. Obviously, we've heard some very important talks on climate today as well, health, food production, and toxics in the environment. So we all know that these are the great challenges that need to be addressed. Yet we also recognize that simply addressing these problems is not enough. In other words, we've seen so many attempts to address these problems. We're doing the so-called right things, but doing them in a fundamentally flawed and unsustainable manner. In other words, we all want to think about how we move toward renewable energy, but I think there'd be general agreement that from a long-term sustainability perspective that perhaps bio-based ethanol has some challenges. We all want clean water for health reasons, but we know that if we clean our water with particular lethal substances, that might come back to haunt us on a variety of levels. If we're looking at energy saving even in our lighting, we've actually recently published a paper on how the mercury content from the lighting may exceed the mercury released by coal-fired power plants, depending on the nature of the energy grid. And of course, when you're looking at, as we all want to move toward renewable sources such as photovoltaics, our choices of the materials that we design may actually be the dominant factor if they're precious, rare, toxic photovoltaics. So what do we think about when we step back and think about how we design our chemistry, and how do we ensure that we're looking to do the right things right? Well, this is the basis of what the principles of green chemistry strives to do. How it looks at the fundamentals across the life cycle and the inherent nature of our feedstocks, our transformations, our target molecules, our separations, so that they are fundamentally sustainable from beginning to end, and thinking about resilience, knowledge of what makes a system resilient, not just in order to describe it, such as with an ecosystem or the internet or an energy grid, but understanding the fundamentals of resiliency enough to use it as a design tool as we implement our next generation products, processes, and systems. And how this is going to be needed in order to bring about transformative generations. Why transformative innovations? Because I think everybody in this room appreciates that when we're looking at the unsustainable trajectory that we are on as a civilization, incrementalism won't suffice. A 25%, 50% efficiency increase is not going to bring about the sustainable trajectory. The Varganagel calculations out of the Wuppertal Institute would suggest that if everybody lived at the same level of development as we in the United States, Europe, Japan, that you would need at least 4 Earth equivalents in order to supply the resources for that state of development. Now, we're not going to get another 3 Earth equivalents, and so how do we understand the basis of our material and energy? And that comes down to this one-sentence definition, which is the design of chemical products and processes that reduce or eliminate the use and generation of hazardous substances. Hazardous being defined as adverse consequence, whether it be physical, whether it be toxicological, or it's global. And so this design paradigm has been playing out over the past 50 years, and it has met with widespread adoption both in industry sectors and the scientific community. Just the tracking of the successes by the Presidential Green Chemistry Challenge Awards talks about how a train car 100 miles long of hazardous substances have been eliminated by just the winners. And this has been duplicated in the UK, Japan, Italy, Australia, etc. We're looking at whole industry sectors, pharmaceutical sector, electronic sector, cosmetic sectors, that are crosswalking their R&D portfolios around principles of green chemistry, and we're now seeing this moving into legislative and policy initiatives, and even our NAS, when it looks at the beyond the molecular frontier, is saying we're not only looking at the manufacturing plants, but also how we are looking at the products themselves, the target molecules themselves. So I don't put this up as an eye chart. I say that these 12 principles of green chemistry, if we were to talk them through, would be all about understanding the nature of our feedstocks, whether they're depleting or renewable, the efficiency of our transformations, whether they're atom economical, whether the nature of our separations, the energy we use, the target molecules, whether they're degradable, toxic, etc. And at the end of this discussion, we'd say, is this straightforward? Yes. Is this common sense? Yes. Are these principles almost trivial? Yes. They just happen to bear very little relationship to how we do things today. When we take a look at how we are functioning today, we recognize that there are whole industry sectors just on cleaning up after wasteful syntheses. We understand that everyone in this room has persistent bioaccumulating substances that are building up according to the CDC, all of us, every newborn child. But I'm not waving my hand saying that we're all going to die and this is an unacceptable risk. What I am saying is that this is a design issue that we as chemists know how to design against. We know how to design for degradability. We know that the vast majority of our synthetic materials When I say vast majority, I'm saying between 96, 98%, depending on which numbers you believe, are depleting rather than renewable. And that many of our issues with regard to safety, security, accidents, and sabotage are dealt with either through engineering and security barriers rather than through a fundamental rethinking of how we carry out these transformations. So I go through this general introduction to give you an overview perspective on green chemistry and how this is a shift from how we've thought about things previously, and shifting it from the circumstantial way of dealing with issues of the environment to intrinsic. What do I mean by that? We've changed the way that we use our chemical substances, the way we handle, the way we transport, the way that we treat and protect people. We put smokestack scrubbers on smokestacks, have people wear protective gear, and all of these approaches to control exposure to chemicals necessarily have two things in common. One, they can, and as a probability function, will fail. And when they fail, the risk goes to its maximum because you haven't addressed the hazard side of the equation. Second, they all necessarily have to be a cost drain. They cannot add performance, they cannot add capabilities, they cannot add efficiencies. When we contrast it with the green chemistry approach, what we're talking about is at the same time that you're redesigning the molecules of the transformation so that they're environmentally benign and more sustainable, you can impart that efficiency, that capability, that new performance into these. And this is why, by building together the inherent sustainability, it will also meet, in many cases, the economic goals that the companies are interested in. So what I'd like to now shift into is a discussion of some of the scientific innovations, first generally, and then in our group and in our center. So when we look at some of the innovations that have taken place over the course of the past decade, it's very broad. I'm old enough to remember when people were saying, "Oh, green chemistry is all about solvents." Then it was green chemistry is all about organic synthesis. Then it's green chemistry is all about catalysis. Then it was green chemistry is all about nanotechnology. And after a while, you start realizing that green chemistry is all about all of these. That it affects the design and generation of some examples shown here. Everything from supercritical fluids all the way through some of our most elegant catalytic work that's too numerous to mention. So I'd like to focus down on some of the specific research that we have going on in our labs at the center, and want to emphasize that, because I'd like to talk about some of our work, that there's certainly quite a collection of work by other research groups throughout certainly chemistry, chemical engineering, our School of Forestry and Environment, everything from some of the wonderful work being done by Brudvig, Crabtree, Batista, and Schmuttenmeyer on some of the photosystem 2 mimics that we'll hear a lot more about today. Some of the wonderful work being done out of the Elamelic group on forward osmosis and new energy efficient ways of water purification. Some of the excellent work being done on microbial hydrogen generation out of the Petchia group. So there's quite a collection that spans various schools at Yale, but I'd like to just take a little time to talk about some of the work that we're doing in our labs right now and tying them to some of the great sustainability challenges. So right now we are stepping back and saying, how do we address some of the challenges of healthcare? Most people don't have a full appreciation that on average, when you're generating, let's say, a pound of a pharmaceutical, on average you're generating about a ton of waste, much of it biologically active, much of it hazardous. So how do you recognize that even such groups as the ACS Green Chemistry Pharmaceutical Roundtable looks at top 10 reactions that are in need of reinvention from a green chemistry perspective. Well, some of the strategies that we've been taking and involve a new look at the benign reagents, coupling, cascading and tandem reactions, and ensuring that we have minimal separation. So we take a look at some of the targets that we're focusing on, and rather than saying how do we look at a specific target and develop or demonstrate a particular synthetic methodology, we look at what are the strategies that are going to open up more skeletal structures, more systems for a wide range of targets that we can control and manipulate as the reaction proceeds. So if you see some of these different molecules, some may look similar, some may look very different, important targets for varying reasons. Looking at how do we use the same approach, the same set of reactions that will give us a wide diversity if we just simply tweak it slightly. I'll go through the example of an old favorite of mine. I say it's an old favorite, retrokinesin, because 20 years ago, over 20 years ago, I had the first synthesis of this natural product that was important to one of our pharmaceutical companies. And it was approximately a 12-step synthesis, and I think the yield was in the low single digits, and I was very, very proud and happy. So we said, how do we revisit this in a different way? And one of the things that we're looking at is a multi-component coupling, cycloisomerization. In this case, we're looking at bringing together 3 components and a one-part synthesis. By looking at this transformation, we're able to generate a wide range of skeletons, some with induced rearrangements, some with some not requiring rearrangement, and we have been able to generate the core of all the colored emphasis on each of these molecules seems to have has disappeared, emphasizing how the core of these different molecules is generated by this coupling and this controlled cyclization. Leaving that as it is, we're able to access each of these molecules with the exact same coupling. When we move from the enine to the diine, we are also able to generate these structures. You'll recognize the parent of the retrokinesin shown here. Now these are this recently published work on the retrokinesin backbone. These are yields that one would normally apologize for, of 41% and 25%, until you look at a comparison between a one-step versus multi-step synthesis, one isolation, and you generate 2 natural products in this one step. We've opened this up to a wide range of this family, and are able to get these in significantly improved optimized yields. A second area that we're working in outside of synthesis is materials. So right now, as I mentioned, the vast majority of materials that we're using in our economy are synthetic materials, are petroleum-based, and in order to impart the properties that we want from these materials, it requires the use of additives that are in the news on a regular basis. Whether it's Arnold Schwarzenegger banning phthalates, or the bans coming out of Europe as well, whether it's bisphenol A that has the Food and Drug Administration and the National Toxicology Program at war with one another. There's a wide range of these additives that make that make some of the materials that we use of high concern. When we look at PVC, some of the ways that we achieve plasticity of our PVC with phthalates are linked to very serious questions of endocrine disruption. And so, while it's easy to talk about, we need to move to bio-based polymers. In order to have these polymers, whether it's polylactic acid or the polyhydroxyalkanoates, in order to have these polymers have the properties that are going to allow them to get into market, we're going to need to be able to manipulate their properties. One of the projects that we have going in my lab, along with the Asuji lab at Yale, is how do you build the, in some cases, plasticizing properties or other properties that you're trying to induce, build that into the polymer matrix rather than having additives that are going to leach out, bioaccumulate, and cause problems. The example of one system that we're developing is shown here with this genericized scheme and the specific application. This is largely stealing from the field of liquid crystal display manufacture and imparting properties on these polymers so that you can tweak them with various either electrical, light, thermal, other impulses in order to bring about the properties when and in the time frame that you want. We're also looking at chitin, the second largest material made in the world after lignocellulose, how you manipulate chitin in order to get the properties through the manipulation of the functionality there, whether it's the amine or the hydroxyls. One of the things that is going to be extremely important is as we go to the naturally based plasticizers, such as the citrates and the sorbitols, etc., how you are able to control this while using substances that are only generally regarded as safe by FDA, especially if you're looking at food packaging. So we look at some of the approaches where we're starting with either such substances as candle nut oil or soy, and going through fairly straightforward manipulations of epoxidation and acrylation with some of these grass substances, and are able to make very high strength composites that, along with our collaborator Richard Wool, are being used in structural features, everything from building materials all the way to panels and automotive usage. So we move on to our third area of renewable energy. Renewable energy is obviously one of those great challenges. And when we step back and take a look at our current approaches to some of our bio-based energy, we recognize that when it's competing with cropland, when it's impacting food prices, when the procedures that we're using in order to grow these crops are unsustainable, and with some of the approaches that are being the papers that are coming out in science about the net carbon production from some of the biofuels approaches, for instance, in Indonesia, Malaysia, etc. We recognize that, are we doing the right things right? So what green chemistry approaches might be able to be used? Well, we're working on a project primarily in Uganda and Ethiopia, where we have about 10,000 hectares of land, and working very closely with our School of Forestry and Environmental Studies, our sustainable forestry capabilities, on how do you take this and make it into a sustainable system. Now, if I were to say we're doing the plantings of Jatropha, Castor, Cimaruba, etc., and we're getting carbon credits for for this project, you'd say, oh, that's a nice climate project. If I said that we are planting these in some of the most arid parts where nothing has grown for millennia and stopping the encroachment of the desert, you'd say, well, that's a nice anti-desertification project. If I said that the seed value, the oil of the seeds, has 4 to 5 times the energy value of soy, I'd say, oh, it's an interesting bioenergy project. If I said that we take the seed husks, dry them, grind them down, use them as natural coagulants to purify very turbid water, you'd say that's an interesting water project. If I talk to you about the phytopharmaceuticals that we harvest from the leaves and use to combat malaria, you'd say that that's an interesting healthcare project. And the point is that this is a hopefully interesting and important sustainability project. And understanding how to step back and look at these interactions as a complex system and beginning to ask those right questions is what this project is most geared toward doing. Now, I'd like to finish up with the fourth area, the one that is just being launched, one that we're perhaps most excited about. That as we look at, when we look at the evolution of toxicology, we know that it has evolved from simply a descriptive science to a mechanistic science, that we moved from just knowing that something is toxic to why at the molecular level it can follow a mechanism that makes it toxic. Because of this, it gives us the design handles that we need as molecular architects in order to design things differently and move toward preventative toxicology rather than just simply predictive toxicology. We also know that in order to receive a PhD in chemistry, there is no requirement for understanding the molecular basis of the consequences or the potential consequences of the tools of our trade. And so is it possible, what we ask is it possible, with the advances that are being made in toxicology and toxicogenomics and molecular understanding of toxicity, can we stand on, I'll use the phrase, on the shoulders of giants from the pharmaceutical field that has given us an understanding of the mechanistic basis of biological activity in order to create a framework for those chemists that are making the other 99% of molecules that are not pharmaceuticals, that are not drugs, so that we impart the properties that we want, that we impart the performance that we want of these chemicals without, at the same time, imparting the hazard and the unsustainability. So that's the challenge that we're taking on, recognizing that we are swimming in data that's currently being generated from some of the high throughput screening, the in silico predictors of toxicity, the genomic signatures, and all of these are of direct relevance to molecular design. Yet the connection between this collection of data and the informing of how we make the next generation of adhesive, the next generation of dye, the next generation photovoltaic is not being incorporated. And so we look to try to make something transparent, accessible, and recognize that as we go from understanding of toxicokinetics and toxicodynamics, understanding how to manipulate bioavailability, to structure-activity relationships, all the way up to mechanism of action, that each one of these approaches gives us a design handle. Each one of these, as we increase in level of complexity and in many ways difficulty, we are able to make impacts on how to design next generation of substances. If we want to look at solubility, certainly manipulating octanol water partition coefficients, blood-brain barrier transport, all the way to gas partitioning in the lungs. If we want to correlate this, the important work of Bill Jorgensen at Yale and rational drug design is a wonderful platform that instead of how do we manipulate a drug so that it is able to get into our bodies, is able to cross the necessary biological membranes, is able to make its way to a target molecule, is able to bind to a particular receptor in order to cause a therapeutic biological effect. We want to tip that model on its head build on the Jorgensen-type models and say, how do we design it so that it's unable to make it into our bodies, cross the membranes, make it to the organ, and not bind to cause a toxic effect. And so we look at some examples of manipulation of things like molecular weight and how those are going to prohibit the ability of the substance to get in and cause that adverse toxic effect. We look at the example of how volatility, simply controlled, a basic parameter that we all know how to manipulate, and yet will have a dramatic impact on whether or not something is going to cause human health and environmental damage as well. We look at examples of how this can and has been used. We recognize that through understanding manipulations, in this case of this cephalosporins, that by using the zwitterion, this is going to be directly linked to the organic anion transporter and whether or not it's going to have biological accumulation in the cell, where if you instead switch to the anionic analog, it's going to move from the blood into the urine, not bioaccumulate, and therefore reduce its neurotoxicity by 6 orders of magnitude. So as we look at this approach, we have the ability to control structure-activity relationships on a wide range of reactive functional groups, and by avoiding, masking, manipulating these reactive functional groups, we're able to dramatically control the adverse impact on the environment. This example of glycidyl ethers, well, I find structure-activity relationships obviously very frustrating because they don't give you the type of mechanistic detail. They do give us guidance that when you have certain correlations, in this case, length of the chain associated with myocardial effects, and in this case, the length of this particular glycidyl ether associated with testicular lesions. You have the design handles, and these are transparent to synthetic designers. Of course, at our highest level, it's all about mechanism of action, and while it gives you far more design options, far more design handles, and it also is a reality that the vast majority of our toxic effects do not have well elucidated MOAs, much less the full mapping of the key events at which structural interventions can be made. But as the genomic data, the toxicogenomics comes in, we are able to constantly evolve and have more design options, so that rather than simply trying to control the circumstances of our chemicals, we're able to design the character and the inherent nature of our substances, regardless of their end performance. So I'm going to just conclude with some of the big questions that are certainly going to be facing green chemistry. If we're going to use chemistry in a way that's going to move us onto a sustainable trajectory. When we look at our feedstocks, will our highest value applications be what we tap into for our limited, finite, depleting resources, and for the vast majority of others, we'll use renewable resources? Are we going to be able to evaluate synthetic design, not simply by Yale, but the degree to which our starting atoms are incorporated into the final product? Are we going to be able to design our catalysts from first theoretical principles and make them multifunctional and also designed for self-separation from product? When we think about our solvent systems, are we going to move beyond simple mass and energy transfer as a reaction medium and instead design some of these substances to be catalytic and enhance separations? And will we design our solvents so that they are obedient and change properties upon imparted stimulus. When we think about how nature carries out many of its transformations, rather than making our substrates more and more functionalized with reactive functional groups, our reagents more and more reactive, knowing that reactivity is, of course, closely linked to toxicity, are we instead going to continue to develop how you impart reactivity at the time and the place that it's needed, much like nature does? And will we move from our command of the covalent bond to a command of weak force interactions, not just simply to explain properties or explain reaction pathways, but as a design tool to impart properties and impart reaction pathways? And finally, I just want to finish up with, will we understand the molecular basis of hazard, and will we be able to design to minimize that toxicity rather than just simply measure how toxic something is? And finally, will we be able to understand, will we be able to complement our reductionist understanding to an integrative system, because what we're dealing with complex systems that need a systems and integrative approach. With that said, I'm not suggesting that these are problems that are not being worked on at all, just that these are problems that are crucial and not being worked on in, quite frankly, in most of the mainstream challenges that we're facing. Thank you for your attention, and I'll be happy to answer questions as time allows.